The topic we're going to look at in this video is called multicollinearity. It's quite a mouthful. I think I mentioned in the last video something like supercalifragilisticexpialidocious. Maybe one of your final exam questions will be how do you say it and how do you spell it? They won't, so don't even think about that. Also, I just remembered I didn't lead in with any music, so you didn't get to hear any of my daughter's crazy stuff. Okay, guys. Anyway, let's get into a little bit of review. I don't want to just jump directly into multicollinearity. One of my resources that I use for this class is DeGroot, and I don't remember the name of the text, but I think it was Statistical Models, Modeling the World, or I don't know. But stealing some quotes from him, he says that we frequently trying to get everything centered here so you guys can see it. Okay. Let me see. We frequently ask 4 important questions about our predictor variables. Now, this is one place that I would kind of like it if we were in class, because I would probably put you guys in groups and have you to kind of talk about this. But just going to pause here just a little bit. Think about 4 things that you think, based on all of your experience with regression models, 4 things that we think are important enough to kind of sit back and question. Now I'm going to help you with one of them. The very first one that comes to mind for me, and the first one that DeGroot, I'm pretty sure it was DeGroot. Don't hold me to that. Maybe I got this out of, no, I'm pretty sure I did. The first thing I would want to know is what is the relative effect of each of the predictor variables. Now, I think that's the obvious one. If I was going to try to predict first-year GPA for a college student, and I looked at their ACT score, and I looked at their parents' education, I looked at socioeconomic status, and I looked at high school GPA, that I would want to know, kind of independent of each of the other variables, what is the relative effect of each of those. So certainly not creating anything here that's of alarming proportion, but that's one of the first things that I would want to think about. Next thing I'd want to know is how much or what is the magnitude how much does each predictor variable have on our dependent variable? Okay. So taken separately. So the relative effect up here, I kind of look at the complete set of predictors overall, how to high school GPA, I forget what I actually said now, ACT, socioeconomic status, and parents' education. And this one, we want to kind of concentrate on each one of them. So collectively and individually, how do these variables serve our model? Next thing I'd want to know, and this has been the motivation for this extra sum of squares stuff, is can a predictor variable be dropped from the model well, let's have a so without let's see, can a variable predictor be dropped from the model because it has little to no effect on our dependent variable. And the fourth thing, again, kind of serving as a motivation for the extra sum of squares sequence of videos that we've been looking at lately, is should any predictor that's not currently in the model be added. Those four things collectively, we want to look at our the impact of the variables on predicting y. We want to look at the individual effect of each of the predictors. We want to see of our set of predictors, could something be dropped without losing predictability, if you will. And the fourth thing, is there anything lurking out there that we should add to our model to better explain the relationship between the set of predictors and y? Now, the answers to these questions are relatively simple. If we have the following. Can you guys see that? Yeah. All right. I think it's a good time to switch over the paper. Yeah, let's get squared up here. Answers to these, if we have the following, so the answers are really relatively simple. If our predictor variables are not highly correlated, number two, our predictor variables are uncorrelated. With the other predictor variables that are not in the model but are highly related to the dependent variable. All right, so again, we want to know that the predictor variables that we've regressed Y on, that there's not high correlation between any pairs of predictors. And we want to know that there's not some variable out there lurking around that's highly related to the dependent variable that we haven't included in our model. And you know what? That's when I was preparing for this lecture, I'm like, did I really tell that? Because I think some of that's just common sense. I don't know not common sense. I don't know what's common sense to really anybody when it comes to statistics. But I think by this time at this time stage of 5,500, 6,500, that should be pretty clear. Now, I tried to come up with an example and to think of something that would demonstrate this. And a few years ago, at least the way that this has been told to me, there was someone, I think I heard it was a researcher, who went to a place called Burgundy, France. And apparently in Burgundy, France, they drink a lot of red wine. And, I heard stories about you would see 1-year-old, 18-month-old babies who would have wine in their bottle. I've never been to Burgundy, France, so I can't say anything about that. But that's the way it is, and that's the way it is. Well, the researcher apparently came back to the United States and wanted to see if there was a relationship between. Okay, let me back up. I lost the punchline here. In Burgundy, France, this particular area of France, for some reason, the people in that region have low rates of heart disease. So a smaller percentage than I guess you would typically expect based on what you would see here in the United States has rates of heart disease. So a researcher came back and thought, and those, I can't do that very well. Rates of heart disease. Those, those questions are usually what's the guiding foundation to substantial research or significant research. So they wanted to see if this was related to the percentage of the population who drinks red wine on a regular basis at moderation. Now, some of those people like me who loves the taste of a good bottle of red wine, I was really cool with that. I thought, oh, wow, cool, percentage of population who drinks red wine on a regular basis, and then they had to come in and put this part, at moderation. Well, all right. So that kind of spoiled the day. So you can't go out here and pound, 14 glasses of wine every night and expect to have this relationship going on. Not that I would ever do that. But so again, the percentage of population who drinks red wine, and I think they actually got this down to 2 glasses per day. Okay, now I have really big glasses, so we bought big glasses maybe for that very reason. Who knows? Now, let's add into this model socioeconomic status. So by adding this into the model, I'm essentially controlling for or adjusting the variation in rates of heart disease attributed to socioeconomic status. So if you remember how the interpretations of an additional variable goes, if I have the percentage of the population who drinks red wine and add in socioeconomic status, then I would say controlling for drinking wine on a regular basis of moderation, 1 unit increase in SES, whatever the beta would be, is the rate of change. Well, my thing there is going absolutely crazy. I don't know if you guys saw that or not, but it kind of flashed. But anyway, I'm sure you did because you see everything that's on my desktop. Now, something out there that they found was frequency of exercise. Now, what I want you to think of here is think about this second thing up here. Is there any predictor variable that's correlated with the other predictor variable that's not in the model? Well, when they just had socioeconomic status and, yes or no, do you drink red wine on a regular basis at a moderation level? There's this other thing that was highly correlated and related to the dependent variable. Well, it turned out that socioeconomic status and frequency of exercise turn out to be highly correlated. And what it turned out to be, at least in the initial analysis, now I do have to tell you, I keep an eye on this for some crazy reason. Imagine that. There's some of the research out now that claims that there is actually some chemicals in red wine that seems to be related to decreased rates of heart disease. But I'm just talking about this initial study. So what happened is you had frequency of exercise, which was highly correlated to socioeconomic status, and socioeconomic status was actually highly related to percentage of people drinking red wine. So at the end of the day, it really wasn't, again, in the initial study, it really wasn't the drinking of the red wine or the socioeconomic status. It was the frequency of exercise that was highly related to these two things. It turns out, at least according to the study, that frequency of exercise and socioeconomic status are related because people of higher socioeconomic status tend to exercise more than people of low socioeconomic status. Having been a gym rat for many, many years, obviously not anymore, but in my younger days, I kind of find that a little hard to believe. But again, that's a restricted population, so I don't want to go there because I don't want you guys to go there. All right, gang, let's bring in the topic of this presentation. Again, this is multicollinearity. And guys, at the end of the day, multicollinearity presents itself when our predictor variables are highly correlated among themselves. Now, I haven't made a big deal about, when we run a multiple regression model in R, checking the scatter plots and the correlation matrix. And I haven't really done it because the reason that we do that is pretty much what we're learning right now. Now, the game plan here is what I want to do is I want to explore the opposite ends of the spectrum. And the spectrum that I'm talking about is the spectrum of correlation. So the very first thing I want to do in this situation is I want to give you a situation where we're regressing y on x1 and x2. where the correlation between x1 and x2, which again is equivalent to the correlation between x2 and x1, is 0. So in this situation right here, we have absence of multicollinearity. The next example I want to show you is y regressed on x1 plus x2, another data set where our two predictors in our model are highly correlated. This is an example of extreme multicollinearity. And ultimately what we're going to see through this is we're going to see that the stability of the sum of squares, or the error sum of squares, turns out to be the issue. Now, let's look at some data here. Just kind of keep it simple. And the y I want you to look at is 20, 18, 32, 15, 11, 25. And the x1 is 1, 1, 2, 2, 3, 3. And the next thing I did is I came up with values that I knew would create a correlation between the two equal to 0. And again, this is all about showing the situation here. In a situation where what happens, and I ultimately want to show you the stability of the error sum squares, but I want to contrast that with the other end. So, guys, anyway, x1, x2, as I'll show you when we get into R, the correlation is equal to 0. Now, what I want to do is I want to keep a running total of our work here, and let's tell you what, let's go ahead and do that. Let's get this started before we jump over into R and do some stuff. Come on, get centered. Here we go. So what I want to do is I want to look at 3 models. And I want to look at, y regressed on x1 plus x2. And I want to look at y regressed on just x1. And y regressed on just x2. And what I want to create for each one of these is I want to create how do I want to do this? Let's do the regression, the error, the total, sum of squares, degrees of freedom, and let's look at the mean square. So I want to look at this for each of the models. All right. All right, guys. I don't have this in CSV format, so we're going to use the old-fashioned way. So I'll tell you what. Let me try to find the data here. Yeah. So, guys, first thing I would do is I would use this C deal that we talked about many moons ago. So 20, 18, 32, 15, 11, and 25. And the next thing I want to create is x1. And that was 1, 1, 2, 2, 3, 3. And then I want to do x2. And 2, 3, 2, 3, 2, 3. Right? Yeah. Now, just to show you, the correlation between x1 and x2, is 0. And just so this is clearly not a proof, but it just demonstrated the correlation between x2 and x1 is also equal to 0. So, gang, what I want to do here is I want to run 3 models. So let's run our first model, and we'll call this model 1. This is going to be our full model. I'll tell you what, I'm going to call this full. So I want to run a linear model y regressed on x1 plus x2. So summary for full will give us our coefficients, and ANOVA for full will give us our sum of squares. Now, I think, is an AOV, is that... yeah, okay. Let's do the ANOVA. So the regression sum of squares will be the sum of squares for x1 and x2. So our degrees of freedom will be 2, and our sum of squares will be 5.167, and our error sum of squares has degrees of freedom 3, and it is 273.66. Actually 0.67. So our total sum of squares going to be 5.167 plus 273.67. So our total sum of squares is 278.84. Okay. And the let's see, mean square will be so we've got 91.22, and then 5.167 divided by 2 gives us 2.58 for the mean square for the regression. Now, let me just show you what I'm doing here. So, if you care to work along with me, I'm just doing this for the first model. All right. Now, next thing I want to look at is I just want to look at the y predicted by x1. So we'll call this model 1. ANOVA. And so let's, I'm going to write this down over here. A little time consuming, but I think it's going to be worth it to see the stability of some things. So, guys, our regression sum of squares is 1, and our degrees of freedom is 1, and our mean square is 1. The error has degrees of freedom 4. And so 277.83. That's easy to add, 278.83. And the mean square would be 69.46. Not really as worried about the mean square. And just to mix it up a little bit, I'm going to go ANOVA linear model y x2. And let's write this stuff down. All right, so sum squares for our model is 4.17. Got a lot of error here, don't we? Degrees of freedom 1. 4.17. Our error term is 274.67. And degrees of freedom 4, 68.67. And our total sum of squares, 4.17 plus 274.67, 278.84. I really debated whether or not to just go ahead and have all this calculated. Actually, I did go ahead and calculate it for this particular data set. But I wanted you guys to see, again, just so there's no misunderstanding on things. Now, what I want to do now, I've got my model, so I want to go in and look at the coefficients. Now, if I go back to my full model up at the top, you can see that my model is under the estimate. So my model are these three things here. So up here, we would have that our model for the full, and I'm going to write this right above the box. So this is going to be y equals, well, actually y hat equals. All right, where are we? 25.33 minus 0.5x1 minus 1.67 x2. All right, got me right here. Beta 0, well, B0, B1, B2. Now what I want to do, I call this next model, model 1. So I want to go summary of model 1. And see the coefficients when we just have x1 in our model. Well, here we have y hat is equal to 21.17 minus 0.5 x1. Now, kind of messed things up here, but it's going to be copy, paste. Let's call this model 2. And we do a summary model 2, and we'll get our coefficients. Whoa. Oh, darn. Let's call this model 3. Got in a hurry and messed up. So we want y on x2. And now summary model 3. All right, gang. So 24.33. So y hat is 24.33 minus 1.67 x2. All right, been writing all this stuff down so we can go back over to this, and let me get all this, where you can see it. Now, notice that B1 negative 0.5 is the same whether, and we just call this stable. The measurement for B1 is stable whether we have x1 and x2 in the model or whether we just have x1 in the model. And also notice that beta 2 is stable whether or not we have just x2 in the model or x1 and x2. So what we can say is that when we have a two predictor model, now I'll tell you what, let me write this down. I don't want to. So kind of a summary that we can say from this is that when we have a two predictor model with x1 and x2 as our predictors, and when the correlation between x1 and x2 is equal to 0, it leads credence, if you will, or at least support for controlled experiments, because experimental control permits us to choose the level of the variable that we want to include in our model. That was really sloppy. Let's write this out. Okay. So I can say strong support for experimental control since this permits us to choose the levels that are uncorrelated. I think that's a much clearer way to say that. Experimental control just means you got control of your design. Now, another important factor is that the sum of squares regression when adding x1 to the model when x2 is already in the model will be the sum of squares x2 minus the sum of squares for the whole model. Now let's go back to R. Now the sum of squares, the error sum of squares when we just have x2 in the model. Where did we have that? Okay, here we go. When we just have x2 in the model, the sum of squares error is 274.667. And then the sum of squares error for the entire model, which is the full model, is 273.667. Well, if my mental arithmetic is correct, that's equal to 1, which is precisely the sum of squares for the regression when x2 is already in the model and we add x1. So down here, if x2 is already in the model, we notice that the sum of squares is 4.167. When we add x2 to the model, you can see that the sum of squares goes up by 1, which is precisely what we just got. The other thing that holds consistent is that the sum of squares, as you would expect, kind of the symmetric property of adding sum of squares. Okay, so we're going to get stability and consistency here. All right, so the sum of squares error for x1 would be right here, 277.83. And the sum of squares there for the entire model, as we just saw, was 273.667. Now let's grab our handy dandy calculator here. 277.83 minus 273.667, and we get 4.163. Now, what that stands for is the change in the sum of squares regression when x2 is added to the model where x1 is already in it. So if we examine the sum of squares regression for x1 being in the model, and that's going to be right here, we'll see that the sum of squares regression is 1, and that's just the other term here. So the 4.167 is added. Well, it's 4.163, but that was just some rounding. So I like to think about that as you kind of have symmetry, and you certainly have stability in the error sum of squares. Now, summary. I would say that x1 and x2 are uncorrelated. The marginal contribution of one predictor variable in reducing the error sum of squares. Is exactly the same as when the predictor variable is in the model alone. Now, let me see if that makes sense. So when x1 and x2 are uncorrelated, the marginal contribution, so the addition of one predictor variable in reducing the error sum of squares, is exactly the same as when the predictor variable is in the model alone. All right, that's perfect. All right, now let's look at the opposite end of the spectrum. And the opposite end of the spectrum is when our predictor variables x1 and x2 are perfectly correlated. Now, what I want to do here is give you a small data set. And 2, 8, 6, 10, and 6, 9, 8, 10. Sorry about that. You couldn't see what I was doing, did you? So we want to look at the mean response, or the expected value, as a function of beta 0 plus beta 1 x1 plus beta 2 x2. All right. Now let's jump into R. I don't know why I worry so much about that paper being centered, but that just bugs me. All right, let's go over into R. And you know what? I actually looked up the other day, found a way to just completely erase R and start over, but I don't remember what that was. I remember it was really easy. And I want to start over here for obvious reasons. You guys want to hear some music? My girls? No. All right. All right. All right. Just to show you what's up here, you'll see that the correlation, and I chose it that way, between the predictor variables is equal to 1. All right. This is going to get fun. Okay. So let's create our model. And we want to go linear model, y as a function of x1 plus x2. And we'll do summary of our model. And we get kind of weird stuff. Now, the first thing it tells us, it examines the residuals, and you know that's fine and dandy. But when we get down to the coefficients, this is one not defined because of singularities. Well, as we've talked about before, the calculation of coefficients is typically performed through matrix multiplication, or at least operations on matrices. And it looks like to me that we get the estimate, the model here, of y hat equals 3 plus x1, but it doesn't include x2. So it turns out that one model is 3 plus x1. No, that's not right. That's 10, isn't it? Yeah, because if you look right here, this isn't scientific notation. It's really strange why I did that. But anyway, that's what it is. So back over here. So that's just going to drive me insane. I can't handle that. Now, let's use our model to predict, and so I'm going to call this model 1, and I'm going to have my y's. Let me go back. Yes, sorry, this is getting kind of clumsy, but I want to do this to show something. So we've got 23, 83, 63. The next one is 2, 8, 6, 10. And x2 is 6, 9, 8. And we're going to look at the predicted for model 1. And leave some space out there because I got more goodies for you. All right, so this model up here, model 1, says that we really don't even need to think about x2. We just multiply x1 by 10 and add 3. So If we take x1 and multiply by 10, add 3, we get 23. And 8 multiplied by 10 gives us 83. And this gives us 63. And this gives us 103. And what we end up getting, we get a perfect model. Now, you're probably sitting there thinking, okay, Darbo, you say this multicollinearity creates issues. And that's the best darn model we've seen yet because it doesn't have any error. Well, let's think about this one. And let's call this model 2. So y hat equal negative 87 plus x1 plus 18x2. So let's do a little bit of work here. So if we put negative 87 plus 2 plus 6 times 18. Douglas, it would help if you turned on the calculator. So negative 87 plus x1 plus 18 times x2, I get 23. And I think, well, that's cool. Not really. But then I put 8 in the model. And I get, well, I'm sorry. I put 8 in for x1. And I put 9 in for x2, and I get 83. And let's put 6 in for x1, and 8 in for x2, and I get 63. And you'll never figure out what I'm going to get for the next one. You got it. If I put 10 in for each of these, I get 103. And again, perfect model, no error. Well, that's, again, kind of weird. We've never seen that before, have we? So, I'll tell you, this one took a while to find. Really, it doesn't, because if... just something I'll show you in just a second. Now, this is model 3, and you probably already know what the punchline is going to be. So let's just run through one of them. I'm not going to bore you to death on this, but so we have negative 7 plus 9 times 2 plus 2 times 6. And lo and behold, we get 23. And be no stretch of the imagination that we get another perfect model with no random error. Now, go all the way back to 5500 when we first started, and we started looking at the ideal model. And we looked at the linear model, the one predictor situation. And we found the least, well, we used the least squares approach. In other words, we've got these data points, and we try to find the unique line that minimizes the sum of squares. Well, again, the operative word there is uniqueness. In this situation, we came up with one line that minimizes the sum of squares. What you'll see here is, and I did this, I just put this in my TI-84 calculator, and what you actually find out is you find out that there is a perfect relationship between x1 and x2 we can always find x2 by using the linear model 5 plus 1/2 x1. So because these things are perfectly related, it gives us actually more than we ever want, and that's essentially infinitely many perfect models. Well, guys, that's obviously not cool. for a variety of reasons. Let's put these reasons and just state them. So conclusions that I want you to take away from this. Number one, when these two variables were perfectly correlated, the result probably wasn't what you thought it was. This did not keep us from getting a quote-unquote good model. If the effectiveness of a model is to make valid predictions, I tell you what, those are the best we've seen yet. The problem is we had many different equivalent models that we can't honestly interpret. I mean, let's go back to, I'm sure you remember how to interpret coefficients. In the first model we have, we control, the first model. Let's do this one right here. So negative 87 plus x1 plus 18x2. Well, this tells us that controlling for x1, when we increase x2 1 unit, our predicted value changes 18 units. However, in the other model, it tells us that when we control x1, when we increase x2 1 unit, the predicted y increases 2 units. So guys, at the end of the day, what we end up getting is when we control one of these variables is we get way too much error. In our regression coefficients. Okay. Now, guys, at the end of the day, multicollinearity it just hit me. I'm writing too small. I'm sure I'll hear about that. One thing I want you to think about is in the real world. It's kind of weird because we're clearly in the real world, filled with real data. Rarely do we find this. Do we find that the correlation between two variables is equal to plus or minus 1, and actually to be quite candid about all this, rarely do we find where the correlation will be exactly equal to 0. So, guys, in other words, rarely do we collect data. That we don't have random error. Having said this, nevertheless, predictor variables may be too highly correlated how do I say this? So predictor variables may be too correlated such that in combination with other predictors, we don't get our model of best fit. All right. Conclusions. Guys, just about to end this video. So again, on this multicollinearity, I've got you can probably tell that I'm kind of stumbling because I'm sitting here looking. I've got an example that I want to get through, but I'm just not going to be able to do it. I'm going to have to put up another video. I wanted this to be the last video before actually you took your midterm, but I'm sitting here looking at what I need to do, and it's not going to happen. So sorry. Going to have another video. So let's just go ahead and wrap this one up. So at the end of the day, we can still get a good fit. Model. If some or all of the predictors are highly correlated. Number 2, inferences aren't affected. And inferences aren't affected as long as there's no extrapolation. So again, talking about this whole multicollinearity thing, again, we still get a good fit. We actually get a whole bunch of models that are good fit. If the models are the predictors are highly correlated. Inferences, and guys, when you think inferences, just think p-values. That's what's meant by that. Second thing, when our predictors are highly correlated, the estimated regression coefficients tend to have large sampling variation. So, and I guess at the end of the day, we could think that just gives us kind of imprecise information. So again, when predictors are highly correlated, the estimated, and I talked about this a little bit earlier. I don't even know really why I'm writing it down, but I want you guys to have all this just for your notes. One of my favorite professors in grad school, Dr. Enochs, at University of Kentucky. The guy wrote down everything, and it's funny how I treasure those notes from his class. So anyway, what am I trying to say here? When the predictors are highly correlated, the estimated regression coefficients let's see, let's just say it this way. We'll have large sampling variation. Fourth thing I want you to know, this is kind of a weird one too. Even though there may exist a statistical relation between y and the set of predictors. Not only the set of predictors, but the predictors individually. Some predictors may not end up being statistically significant. That creates all kinds of issues. Anytime we get bias in our results, that's it's not cool. And a bias is, at the end of the day, it's just defined to be the difference between what the truth is and what we find. So obviously that would be an issue. And then the final thing, just as I pointed out before, is the traditional interpretation of our regression coefficients. Is unreliable. Let's go back to the body fat, and I want you to revisit our model there. And the model that we came up with, for the most part, was this one. And again, just talk it through. If we're going to interpret the tricep coefficient, we would say controlling for the thigh and mid-arm measurement, the predicted body fat will increase 4.3 inches. I believe that's what it was measured in. No, body fat was not inches. Body fat was, I'm not sure of the unit, but anyway, the body fat will increase 4.3 units with each 1 unit increase in tricep. So, guys, we go violating or creating multicollinearity. This is an issue. And the problem actually becomes when these things are actually related. The problem is holding one constant. So think it through. If two things are highly related, how do you hold one constant without affecting the other one? And I found this example in one of the books. Actually, I think it was DeGroot, but it may not have been. If we're looking at a two predictor model of crop yield, Hours of sunshine. And we want to hold amount of rainfall constant. Well, I'll tell you what, it's probably better to look this way. Hold the amount of hours of sunshine constant. Well, the amount of rainfall, although I have seen it rain with the sun out, therefore increasing the hours of sunshine, typically when it rains, there's no sun because to create the rain, it's clouds, and clouds hide the sun. I'm glad you guys, you're probably really happy that I cleared that up for you. So, guys, I'm getting slap happy. It's time to end. So sorry, I didn't get through everything I wanted to get through. I think in the last video I told you there'd be one more. I'm seeing now there's not going to be. There's going to be one more on top of this because I want to go through a full example. So guys, have a good one. Take care.